So we've been doing a lot with logarithmic equations and exponential equations, working with their graphs, understanding their properties. And we're going to begin to kind of put that all together here and work with solving problems. In this video, we're going to solve logarithmic equations algebraically. Our objective to solve logarithmic equations for a specified variable. We know a lot that's going to come into play here, because so we have a pretty big toolkit, and it's going to call on us to use various parts of this toolkit to meet our objective. So what do we know? We know what a logarithmic function is. Any function of the form y equals log base b of x, where the base b is positive and not equal to 1, the argument x is also positive. We know that the log function, when we take the log of something, we get an exponent out of that. The log function outputs an exponent. We know that the exponential function y equals b to the x and the logarithmic function x equals log base b of y are inverse functions, which means they undo one another. So if we're trying to solve something, we can use the inverse function to undo the given function. And we know these properties of logarithms, log base b of 1, 0, etc. This is the product property, this is the quotient property, and this is the power property. So to solve these logarithmic equations requires knowing I'm going to introduce you to two more properties or two more rules that'll help us to solve these logarithmic equations, okay? I'm going to introduce you to the equality properties or the equality rules, and they're simply this. If m equals n, then the log base b of m equals the log base b of n, okay? So in other words, you can take the log of both sides. If you have two numbers that are equal or two things that are equal, you can take the log of both sides and not change the equation. The one we're going to use more often is number 8 here. If you have the log base b of m equals the log base b of n, if the log of the same base, if they're equal, but the arguments are different, then the arguments are equal. In other words, in my high-tech math lingo, you can untake the log of both sides. So if you're given two expressions that are equal, you can take the log, same base, of both sides. If you're given two logs, same base, that are equal, you can untake the log of both sides and set the arguments equal to one another. So, as we work with log equations, the goal becomes usually one of two possibilities. Get a single log on one side of the equation so that you can change it and use its inverse exponential form. So basically you're up here. Once you get a single log, you can rewrite it as an exponent. So I'll put down here, this is number 2 above, okay, right up here. The other thing you want to try to work, the other way to try to solve these is to use the second idea. If we can get a single log on both sides, again like this, then we can use the equality property and just get rid of the logs. And then we can solve the equation. So we'll see some examples of both of those things as we work through a few here. So give me just a moment. I've got 3 examples for us, plus one that kind of has a slight curveball, so you can see how it works. Okay, so in the example 1 here, we want to solve for y in terms of x. So y equals x somehow. Log base b of y equals log base b of 6 minus log base b of x. Okay. Difficult to get a single log on one side because I got logs on both sides. But I can use, this is a difference of two logs, so I can use the quotient property to make the right side 1 log. And then I have log equals log, and I can use the equality rule or the equality property and drop the logs. So I know I can work with this because it's a difference, and I can write the left side is still the log base b of y, but the right side is the log base b of the quotient, 6 divided by x. That's the quotient property or the quotient rule. And so I'll jot that down for you. The quotient rule or quotient property. Now I have log base b of something equals log base b of something else. Well, they're both the logs, they're both the same base, so I can untake the logs and I can drop them. Y is equal to 6 over x. Okay, and this is the equality rule. And I'm done. I wanted to solve for y in terms of x, and I just did. Y is equal to 6 over x. I'm all set. Okay, so I had to draw from these two properties or rules in that problem. Example number 2. We want to again solve for y in terms of x. Well, I've got pi times the log base 4 of x plus the log base 4 of y equals 1. Well, again, here's an example where if I can get these 2 logs into 1 log, I can rewrite them using the exponential form, using the inverse. Well, let's do that. First off, I know I need to, before I can combine them, I got a plus, so I know I've got a multiplication possibility here. A log plus a log is multiplication, but I first need to move this pi back using the power property. So this would be the log base 4 of x to the pi plus the log base 4 of y is equal to 1. And so I used here the power rule or the power property. Now I've got a log plus a log, and I can combine those into 1 log using the product property. So this is the log base 4 of x to the pi times y equals 1. 2 logs being added is the same as the single log of the product. And this is the product property or the product rule. Well, now I've got a single log on one side equals a number on the other, and I can now use the inverse. I can change it to its exponential form. 4 to the first power equals x to the pi times y. So exponential form, base to exponent equals argument. And I'd get rid of that single log that way. This is rewrite. I'll just put inverse. The exponential is the inverse function. The inverse function is the exponential function to the log function. Now I need to solve for y, so I'll divide both sides by x to the pi, and I have y is equal to 4, because 4 to the first power is 4, divided by x to the pi. It looks like a funky mess, but that's indeed the answer. Okay, that's indeed the answer right there. Hope I did all that right. Pi. Yes, we're good. So it's easy. Now you can drop, when you have a single log equals something that's not a log, you can use the inverse function, the exponential function, to rewrite it and then solve it that way. Okay, let's take a look at an example that has a small thing to be aware of going on. I'll slide this up a little bit for us. Example 3. I want to solve this, and I want to solve it for x. So I've got a natural log of x plus 2 minus the natural log of 4x plus 3 equals a natural log of 1 over x. What a mess. But I know my thinking. If I can get one natural log on the left, I'll have one natural log on the right, and then I can drop the natural logs. But first, I have a difference of logs. Let's use the quotient property. So this is the natural log of x plus 2. Whoops, I'm miswriting it. I'm miswriting my quotient property. This is, let's try that again. The natural log of x plus 2 divided by 4x plus 3 is equal to, the natural log of 1 over x. So this is my quotient rule, okay? So I was able to combine these two. I didn't have any number, there's a 1 in front, but I don't have a 2 or any other number in front, so I can use the quotient property of the quotient rule right away. Okay, well, natural log of m equals natural log of n, so I can drop the natural logs. That works. So I have x plus 2 divided by 4x plus 3 equals 1 over x, and now it's just this is the equality property or the equality rule. So now I just have an algebra problem. Got to get the x's together and get 1x, etc., or find some way to solve this. I'm going to multiply both sides. So I'm going to multiply this side and multiply this side. Multiply both sides by, I'll tell you what, let's write them down, make it so you can see it. I'm going to multiply both sides by the denominator. So I'm going to multiply this side by x times 4x plus 3 and multiply this side by x times 4x plus 3 because I want to get rid of those fractions. And that will undo that, and I'll have, let's see, x times x is x squared plus 2x on the left. And I'm skipping a few steps here. The x will undo that. That comes out, and I'll have 4x plus 3 on the right. Well, I see a quadratic forming, so let's get my x's. Let's get everything over to the left side and set it equal to 0 to solve a quadratic. So I have x squared minus 2x minus 3 equals 0. I notice that this quadratic is factorable. So I have x minus 3 times x plus 1 equals 0. So I have x equals 3 or x equals negative 1. And I think those are my two answers. I have two possibilities here. However, you should check your answers. Okay, let's remember that in log function, my arguments must always be positive. So let's check 3. 3 plus 2 is 5. This argument is positive. 4 times 3 is 12, plus 3 is 15. That's positive. 1 over 3 is 1/3. That's positive. So that answer's good. That answer, I could even put it in my calculator and check it. Okay, you should always check your answers if you can. And when you have an equation, you can always check your answers. Now let's check negative 1. Negative 1 plus 2 is positive 1. My argument must be positive. That's good. Negative 1 times 4 is negative 4. Negative 4 plus 3 is negative 1. Not happening. You can't have a negative argument in the log function. So the negative 1 doesn't work for this one, so the negative 1 is out. Let's go ahead and check the negative 1 over here, and we'll notice that negative 1 over here results in a negative 1, another negative argument. So the negative 1 doesn't work here or here. Doesn't matter. It just can't work in one place. So that, even though it worked in the quadratic, it doesn't work in the original equation. So only x equals 3. So moral of the story here, check your answers. Make sure that they work in the original equation. So we did a fair amount of working with our properties to solve logarithmic equations algebraically.